All right, guys, stay in your groups, but look this way real quick. We're going to talk about the first three, and I'm going to give you a little hint on the two of the last ones. I'll let you guys work on those for a little bit. Yeah, I'm going to get away from those. All right. Did anyone get anything for this one? Yes.
I got a technique that. Are we talking about the error or the technique?
Yeah, I think we all get the error.
Yeah.
Okay. Go ahead. What's your technique?
I said if the number is tracking from 100 doesn't end in a zero, rounds to the nearest tens place, so you know what place the tens you're going to get in when you.
I sort of see what you're saying. So you would round
Up
27
to 30.
to 30.
Subtract that from 100, you get 70.
So you know it's got to be in the 70s. And the beautiful thing, yeah, go ahead.
Subtract the 30 from the 23 or 22 to 30.
27. All right. So
Oh wait.
let me
It's
take
27,
your.
never mind.
I think you might do this. Does everybody get what she said? So round 27 up to 30. If I do that, how much more am I subtracting then?
3 more.
3 more. So keep that in mind. Stay right there. 100 minus 30 is 70. So I actually have 73. Right? Because it's 3 higher. I want this to make all the sense in the world. If I subtract 3 more than I was supposed to, I could just add 3 back on at the end.
Yeah.
So you kind of take that 3 out of the way for a second, and then you bring it back in. That's fantastic. I'm almost certain more of you guys have done that. You just didn't necessarily think that way for this problem, maybe. Yes? No? I can't. Some of you guys, when you look at me, I have no way how to interpret how you are looking at me. Okay. Here's my way. That way is beautiful. This is not better, but this actually is kind of interesting. Jeff, write the problem down. What does subtraction really mean? It tells me what about the two numbers. It tells me how far apart they are, correct? Stay with me now. If I made 100 become 99, to keep the distance the same, I better make 83 become, if I make 100 become 99, didn't I get closer? I really want this to make sense. If I make 100 become 99, is the distance, I better move this one a little over that way, yes? So if I make 100 become 99, I want to make 83 become 82. Then they are the same distance. I really want this to make sense. Let me draw it out. So I've got 100 and I've got 83. There's a distance there, right? If I make 100, if I take it down to 99, to keep the distance the same, I better take this down to 82. Isn't 99 minus 82 a much easier problem?
Yes.
Because you don't have to borrow anything, right? So that's 17. No? Maybe. All right, so you can do it the other way. These are both valid methods, right? Well, I really want you to watch this. Why does this problem suck if you had to do it by hand? 1 minus 0.9127. If you had to do this problem by hand, 1 minus 0.9127. What do you have to put after the 1 to make this?
Lots of zeros.
Lots of zeros, and that really sucks. Does everybody agree with me? Agree. Do you agree with me? Maybe? Yes? All right, I can do the same thing. I can make that become 0.9999, and I can make this become 0.9126. If I move them both by 1, they're the same distance. What does that mean? That means the subtraction is the same answer. It's a beautiful way to do this. So then, I just got to, and there's no borrowing because everything's freaking 9s on top. Yes?
Why are we subtracting from 83 in the upper first column? It's 27.
Oh, it was 27. I had it backwards. I had it the right way the first time. Adding. So the method still works. So it should be 100 minus 27. You can make that 99. You can make that 26, and it's still, 73.
That makes more sense.
Okay. My bad. I just saw the 83 and I ran with it. But this guy here is really, really useful right there. Right? All right. Let me do this again for you guys. So we'll do this right. 100 minus 27. You can make this 100. You can make this 30. And you guys got that 3 extra, right? So when you get 70, you bring that 3 back in, make 73. That is the method that May talked about. And then I've got the other method. It's not really my method, it's just the way I was shown. You can make this 99, you can make this 26, and you still get 73.
That's what I was kind of thinking.
Okay.
But kind of.
I just had the 83 in the wrong place, I'm sorry.
Yeah, kind of.
All right. Okay. Now, this one tripped a lot of people up, but I think you might have overheard me, or maybe some of you guys figured this out. This is really just asking you factor these things, correct? This is a sneaky way to bring up the topic of factoring without saying the word factor. So they do 52 for the most part, and then they ask you about 24 cards. So it's really just how many ways can you factor 24, right? You can have one row of 24, yes? And then of course 2 of 12, 3 of 8, 4 of 6, and that's basically where it starts to repeat, right? Okay, I like it. Do you guys see how the highest I can go is 4, and then it kind of starts to repeat? You guys with me? 1 times something, 2 times something, 3 times something, 4 times, and then it turns around, then it repeats. So it kind of limits how many there can be. So if I had a question somewhere that's like, who's got the most, I want to have the least limits. Yes? Sorry? You're good? Okay. So, of course, what about 49? Now, technically, real quick, technically there's how many rectangles here? There's 4, but you might as well just say 8, because you make a 1 by 24 or a 24 by 1, yes? So I would sort of count that as a separate one. So I would say there's 4, but times 2 is 8. So you can double each one. And 49, you got 1, 49, and then you got
7 and 7.
7 times 7, which is where the question about squares came from. I like it. That is a special rectangle. So there's 2, but you can double that because you can turn them both around, so there's kind of 4 there. So did anybody think they got the answer to this one?
I tried. In total, I got 10 rectangles.
For what number?
48.
48. Okay, 48's a really good candidate. Yes.
36 also has 10 rectangles.
Well, let's see, 36. All right, let's take a look.
Oh wait, no, 'cause
No.
6 times 6.
There you go, there you go. So 36, it goes 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6, and then it turns around. 48 is going to go up to 1 times 36. Yeah, this has got what? This has got 10.
Well, if
No,
6 times
because
6
6 times 6 would be.
Oh, that's right.
Same,
It's-
so,
when you turn it around, it's the
1
same
times
thing. I'm with you. This has got
49
9. I like it.
4.
48's got 2 times 24, right? 3 times 16, 4 times 12, 6 times 8, and there's no repeats. Yes?
1 times 36 is a 48.
Oh, sorry. Please help me with my multiplication. I'm not that good with math. Now, did that one make more sense now? It really is just factoring. That's really all it is.
No, he doesn't. One number would be less than 52, so that would be 48. How did you get 48?
48. It's got to be, it's got to be a larger number so that up to like 8 can go into it, it's up to 6 or something.
What I realized 24 already had 4, but I don't know if this makes sense, but 24 already had 4 factored.
Oh, I see what you mean.
So I
So
just
then
doubled
double, yeah, exactly. So it can't be a lower number because then you're missing 2 times that lower number. Does that make any sense? So if you say 24, 48's got to be better. That's sort of like your reasoning because then you get an automatic 1 more factorization. Okay. And then, all right, this one might be a little strange. I don't know if you guys understood. Of course, there should be a closed quote there, but a student says, if I want to divide 21 by 6, I just keep subtracting 6. Do you understand that his method is not wrong necessarily? It's just the way he's interpreting where the answer comes from. It sounds like, so if I subtract 6, that'll be 21 minus 6 is 15 minus 6 is 9 minus 6 is 3, and then he's going to say 3 is the answer.
Yeah, 3 is not the answer.
which is not quite right, right?
This never made
But
sense.
how could you use his method to actually get the right answer? His method will work. Yes?
Okay, so I did like 21 minus 6 is 15, minus 6 is 9, minus 6 is 3. 3 is the remainder. 3 over 6 is 1/2, so it's 3.5.
3.5, 11. So the number of times you're able to subtract, because again, what's multiplication? Repeated addition. So what should division be? Repeated subtraction, dude, or related to it at least, right? And then you can always have this possibility that you have these little stragglers. In this case, you got 3 left over, which is what we say when we have a remainder. We got so many left over. But what would we say? I mean, one thing, I love it. One way to respond to the student, say, well, no, here's the right way to do it. But what's the correct way to respond to the student? I mean, was he totally wrong?
Like, it's a good approach and it works in a way, but like, it won't give you the entire answer until at the end. Like, once you reach the end, it gets complicated.
Yes. And it's all about interpreting his work. What's the correct interpretation of what you've done? What's another thing you might want to tell this person if you're starting to move into like 1427 divided by 9 or something? Is this a good way to do it?
It'll take too long.
Shit, no, right? And but it depends on where you are, right? What you're about to get into. You could say, well, that works for now, but once you get bigger numbers, that might take you a while to do it that way. Okay. So, I don't know. Did anyone sneak a peek at these? Okay, 4 looks weird, but it should not be that bad. Let me tell you something about 5 real quick. Okay. I want to make sure you understand. If I make a times table, do you see how I put the operation right there?
Yeah.
You've all seen this before. So what goes here?
1.
Holy shit. All right. 1, 2, 3, 4, right? And then of course 2, 4, 6, 8, and so forth. How would you show this is commutative?
Are you talking about number 5?
Number 4.
Oh.
I am talking about number 5. Do you see how it's the same thing? What's the operation we have here though? Omega. They tell you how to read it, right? Okay. So what would we say here? You say 2 times 3, right? Because that's times. We're going to say 2 times 3 is 6, and 3 times 2 is 6. Isn't that sort of evidence, not proof yet, but it's evidence that is commutative? You with me? Okay, so that should help you. How would I say this? A omega A is B. All right. Is that weird?
Yes.
It's weird for so many reasons, correct? But what the shit does plus mean? The word plus. P-L-U-S. I mean, we just put letters and say, okay. And then we made a symbol and we explained what it means. And when I see a plus sign, I don't give a shit about it. I don't think twice about it. I know what the hell it is, correct? Of course you do. Could they have made this the symbol? Of course they could have. They totally could have made this weird little squid-looking thing the symbol to mean plus. They just didn't. They wanted to use a stick and another stick. And then they fell over and like, oh, sweet, that's times, right?
Would 1 omega 1 be just what?
No, there's no, all right. So these are to represent just elements. So what do we use plus on? We use them on numbers. We can use them on whole numbers. What do we use times on? Same thing. So when I'm at my multiplication, I have the set of things that I'm operating on. This operator works on A, B, C, D. Let me ask you one question real quick. Is it closed? Is there any answers that are not A, B, C, D? Do you understand? I really want this to make sense, right? It is closed. It's closed, because all the elements I know is A, B, C, D, and do I ever get an answer that is not A, B, C, D? No. Now think about this. How would you show that it's not commutative? What would you have to show? Here, let's do this one together. What is A omega B?
But wait, how does A omega A get B? I don't understand.
All right, help me out. What does that table say? What is 2 times 3?
2 times 3 is 6.
Where did you look in the table? I know you know it, but let's look at the table. Where would you look in the table to see 2 times 3 is 6?
The
3 right
2
there, and then the 2.
times 3 is 6.
Yeah, that's what I
All
was
right.
saying.
Stay with me. This table is the same thing. So what is A omega A? It's B. The same exact way. And I know you guys, this is just like blueberries and pancakes. This is the way things could have looked. We could use the symbol A to mean 1. We could use the omega to mean who knows what. So what is A omega B? B. And what is B omega A? Does it look like it's commutative? Does it look like it's commutative so far? Yes.
Yes.
Can you guys really quickly see? Do you see how A omega B is there and B omega A is there? Can you see where to look to find somewhere where it doesn't do the right thing?
C and D. C and D would be A on one side, but then D and
Yeah, right,
C.
see? Do you see that she's looking at the diagonal? Yeah? That's the result of BA, and this is the result of AB. Well, look at this. Aren't these different? Isn't this D omega C? Are you? I love you guys. Stay with me. You got to be with me in terms of how to read this, because it's just like a times table. A omega A is B. What is D omega C? It's A. Yes? Do you see that? D, operator thing, C gives you A. What does C omega D give you? D. Oh shit. So it's not commutative. I like it. But you see the pattern in the table. I could look at the diagonals to kind of get an idea where it fails. Okay.
So then therefore it's associative.
Well, all right. No. It's not an either or thing. What do you guys think? Do you think it's associative? It's not commutative. What would I have to check to see associativity? So we can pick something like, let's do some with the C's and the D's because they seem to be having trouble, right? C omega D versus C omega, oh crap, I can't even make the right symbol, omega D. Poor little dude. Oh, you guys are loving this, I can feel it. Again, is this a real operator I'm telling you about right now? No. It's an interesting idea about looking at a different, so this operator is defined to do this. This is what it does. So in that level, it's like plus and times, right? Just, we're not used to looking at letters. So what is C omega D? C omega D is D. And then what is D omega D? Let's keep going, Jeff. So C omega D is D. And what is D omega D? D omega D is C. So what is this? Where would I start here? Right? What's D omega D? Is C. What's C omega C? Is C. So that came out the same ocean, right? So then we have to keep going. We have to find another example. Right? So I'm pretty sure this is not associative, but I feel like we should probably move on. I might have been pushing the envelope a little too much on that one. Sorry. But I really want you guys to understand this is the same as this. These are the same things. Yes? So the only way it could be associative is if this works for everything. If this works no matter what you put into it. Yes. Okay. But let's leave that there. I have a feeling you guys are over that one. Number 4 is not as hard. I really want this little dude. What do you want to call this little dude? And you maybe keep some of your decisions to yourself. Yeah, you can call it delta. Some of you guys might know that's the delta symbol, right? So we'll go ahead and call it delta. In case nobody knew, I was going to call it tri for triangle. But so A delta B does this. And they give you an example. 4 delta 5, twice the first minus the second. That's what it always does. So can somebody very quickly show me that it's not commutative? You have, so in order to be commutative, what would have to be true about 5 delta 4? It would have to equal what? If they were commutative, these two should be the same. Yes, that's what commutative means. Do this. Calculate it real quick. What does it do? It doubles the first one and subtracts the second one. That's what it does. Yeah, so this will be 2 times 5 minus 4, so it doubles the first one, subtracts the second one. 10 minus 4 is 6. Are they the same? No. So that shows it's not commutative. Cool. There. There. Because again, remind me, why is addition commutative? Because 5 plus 3 equals. Why is it commutative?
3 plus 4.
Yeah, so to show this is commutative, 4 delta 5 would have to equal 5 delta 4. So that's all you have to do is show that that's not true. They don't equal each other. So it's not commutative. Okay. All right, I'm getting the feeling, let's just get away from that for a second. Let me show you guys something that I know you enjoy. Let's watch some kids do some shit, yes? Let's watch some kids do some stuff. And then we'll do one more thing and then we'll head out. Okay. We'll turn this guy over. Okay. Here we go. So they always show us the problem and then they give us, hopefully the volume is good. Let's find out. Got that? Yeah.
All right, so there are 12 players on my soccer team, and the uniforms cost $27 each. If the coach goes and buys all those uniforms, how much money did he have to spend?
Okay, so there's 12 players. And they're how much? $27?
$27 each.
That would be $324.
Okay, how did you multiply?
Well, if he has 12 players and each player needs a jersey and they're $27, you would just multiply because it's repeated addition. Multiplication is repeated addition, so 27 12 times.
Okay, all right, very good, thank you.
Now that's an example of something that we can really take for granted for us. I mean, that's pretty quick. But that idea of where multiplication comes from, right? What kind of problem leads to multiplication? That's something that you have to learn. So the repeated addition leads to that kind of word problem, telling them to do multiplication because they know it's the same amount 12 times. Basically what she said at the end there. Okay, I like that one. Let's see. Oops, get back there. Oh, first grade. The little dude, I think it's the little dude. Let's see.
Keiko has 12 goldfish. She put the goldfish into 3 fish bowls with the same number of goldfish in each fish bowl. How many goldfish are in each fish bowl?
So she wanted to put it in evenly. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. 12. How many fish bowls did she have?
3.
3. So 2,
So how many fish in each fishbowl? 4. I see just how you did it.
Look at that. You gotta love that kid. All right. So that's what we're about to get into is division, and there are two main kinds of problems that lead to division. There's one that's called sharing. So you have a set number of things that each get part of the whole, which is basically what just happened. And then there's the one where you're dividing. The name just went right out of my head. What was it? Sharing and caring. No. Sharing and oh, that's why it went right in my head, because unfortunately this is sort of something we saw earlier. There's one called measurement. So we're going to see. I think this next one is an example of measurement. Let's see if I remember correctly. Yeah, I think so. Let's see. Yeah, well, it's right there, Jeff. Look at that. So watch the difference here. So in this case, you don't know how many groups, but you know how much.
So there are 20 children are being driven to a park in cars, and each car has only 4 seatbelts, so they can only have 4 kids in each car. How many cars are needed to take all 20 of those children to the park?
Alright, now real quick. Is anyone uncomfortable at all watching that? Do you feel like you should have said something or something? So I think you did great. You let the little student sit there and think about it. You don't want to intrude until they do something like what he just did. Then you ask him, what are you trying to do? But he's going to kind of give it away.
I just lost count.
Yeah, go ahead.
Yeah, so then you know what he was trying to do. He's trying to do the whole problem in his head, right? So now that's why you kind of back off, let them try. You got to tell it wasn't that he totally didn't know what to do.
These are that was part of that. Okay. I see how you did. Thank you.
So, all right, so you remember the one little dude, he had set, he kind of had, I'm gonna show you an example in a minute, but he kind of had a set number of groups, and he kept adding more to each group until he got to the total. Whereas this one, you know how many's in each group already, so you just keep bringing over as many just to see how many groups you end up, okay, sorry. It's kind of like the same problem in 2 different directions. I think I have one more. Oh yeah, this is getting a little ahead, but let's hold off on that. I'm not going to show you that one today. So let's do this. I want to show you one thing about division. And then I think we'll call it a day. If I can find my. Here we go. Division. This is still section 3.2, by the way. Oh, let me show you a picture here. Page. Oh yeah, okay. Real quick. Here's what I'm talking about. See if I can do this without showing you the little answer at the end. So, 2 problems. A class of 20 kids to be divided into 4 teams. How many are on each team? A class of 20 kids divided into teams of 4 children. How many teams are there? That kind of captures those 2 different approaches, right? One. Sorry. Oh, frozen. Oh, well. Crazy thing. So there's one that's called sharing, and that is the first one. Where'd you go? Here we go. So the first one, it's like 4 teams have to share 20 kids. So that's kind of obvious why they call it sharing. This one, 20 children divided into teams of 4. So you're kind of measuring out how many of the 20 can go into each, yes?
Would that be like grouping?
Grouping?
Like another word for grouping, because they're grouping.
Oh, like counting the number of groups in a way, yeah. But grouping, I always think about factoring, yeah, right? The grouping method? I don't know, okay. But real quick. For example, let me do a problem sort of like they just did. Got these, I just want to play with these. Alright. So if I had to make, so let's say I've got 20, so let's see, 4, let's count 20. Jeff, you can do it. I think there's 24 here. Okay, so that should be 20. Let's find out. 4, 5, 6, 7, 8, 9, 10, 11, 12, 20. Okay, so I got 20 people. And I want to make teams of 4. How many teams would I need? So you already know the answer, right? 20 people, teams of 4.
5.
We know it's going to be 5. How would I show that with these? 20 people, I want to make teams of 4.
You would take 4 away. How many times
Yeah.
are you left with 0?
So this way is kind of nice because you already know you can only deal with 4s. So you're basically breaking it up. And this is why this is called the measurement approach. I'm measuring it out into groups of 4 at a time. It's sort of like measuring flour out into cups at a time. So I got 4, 4, 4. There's the 5, right? Just like the little dude did it just a minute ago. There's the 5 groups. Now, what if I said I have 20 kids and I need to, what was the way I just said it? Put them into groups of 4, right? This is a very different approach, but it's the same answer, yes?
Mm-hmm.
How many groups would there be if I had to put them in groups of 4? 5. So both problems are 20 divided by 4. So if I have to do groups of 4, this is what the little dude did. I like what he did. He kind of put 2, what did I just say, 4 groups? 2, 2, and then he just kept adding. I think I just said it the wrong way around, but he kept adding. Remember this? He just kept doing this? Adding some more to each until now he knows there's got to be 4 groups. They've got to have 5 in each group. All right, I just had the same thing happen to me that happened to the little dude. All right. Maybe. So again, it's very subtle, but it's going to be huge when they're first learning this stuff, the difference between those 2 approaches. We know it's 20 divided by 4 each time. Okay. I think I just said that was the last thing, but it isn't. One last tiny little thing. This is, I already said this, so this is, I'm not counting this as something else. I've lost my pen, so sorry. I'll use this one. So if A divided by B is C, let me show you something kind of different. A divided by B is C if and only if A equals B times C. I don't know why that was so pathetic up there.
B times C.
Yeah, right. So what is 6 divided by 2? That's 3, because 2 times 3 is 6. So real quick, I just want to make this the last. This book is so awesome. This is one of the few books I've ever seen actually say this. What is 6 divided by 0?
0. Non-existent.
It would have to be a number. Now listen, what would it have to be? It would have to be a number like this. This is 3. Why? Why is that defined to be 3? Because 3 times 2 is 6. Whatever answer this is, it would have to multiply by 0 and become 6, yes?
Nothing.
Is there anything defined to do that? No, because anything times 0 is. So what do we call it then? undefined. So that explains two things. Why is division by 0 no good, and why is it frickin' called undefined? Has anyone ever been told why it's called undefined?
Probably once, but I forgot.
Understood.
Maybe once and maybe.
Understood. So that's why it's undefined. 3 is defined to be the number that 6 divided by 2 is, because 3 times 2 is 6, but there is no number defined in a way that this will work, right? You can't multiply by 0 and get 6, and of course that's why we call it undefined, and that is officially it for today. Okay. Crazy. So we just got through section 3.2. We'll finish up chapter 3 on Thursday. So we're ready for that quiz the following Thursday. Thanks, guys. Let me know if you have questions. Yes?
When our